So now it gives me a great pleasure to introduce Professor Rob Simcoe. He's a native of Massachusetts, and he has been making telescopes since he started as a hobbyist in the 6th grade. Yeah. And then as an undergraduate, he moved on to bigger telescopes. He participated in the development of the photometric camera for the Sloan Digital Sky Survey. At Caltech during his graduate studies, he worked on construction of a prime focus camera for the 200-inch Hale telescope at Palomar Observatory. And he completed his thesis work on chemical enrichment of the intergalactic medium using the Keck telescopes. Came back to MIT as a Pappalardo postdoctoral fellow and then a faculty member. Worked on the Magellan telescope, including installing the Fire infrared spectrometer, which played a key role in the exploration of cool stars in the nearby universe, and in the discovery and characterization of high redshift quasars, measurements of intergalactic matter in the first billion years after the Big Bang. 2019, he's named director of the Kavli Institute, and he was recently granted 100 hours of time on the James Webb Space Telescope, which I'm just going to talk about tonight. And so with that, I will hand it over to Professor Simcoe.
All right, thank you so much, Megan, for the nice introduction. It's so nice to be here and see everybody. Special welcome also. I was really happy to see a bunch of people with their families here. So we have a couple of generations of people from our youth all the way to seniors, and it's really awesome to see all these nerds in one place. And also online, roughly equal number of people. So just so you know, we're trying to do this on a share through a share so that people on Zoom and people in the room can see. So we'll, as I understand, this is the first time we've done a truly hybrid version of these. So so good luck to us all. And also, I should say, usually for these talks like this, we've rehearsed them over the years and things like this. But this is the very first talk of this sort that I've given about the James Webb Space Telescope, because it's, as you know, it's brand new. And what I want to do is share with you some of the excitement surrounding the early observations that my group is doing with this, and give you some background about the observatory, sort of how we came to where we are today. So the main topics of this are going to cover, first of all, why the James Webb Space Telescope was built. I didn't work on building it, but I sort of followed as it went along, and I came to this involvement in early observations through colleagues who had worked on its early conception starting in the 1990s through today. And then we'll talk a little bit about the journey that led to its launch and successful deployment, as many of you probably followed over the last 9-10 months now, since Christmas of last year. And then at the end, the fun part is that I want to show you a peek at some of the early data that we've gotten using the telescope. And this is the part that's like super new and hot off the presses, so it will be a little interesting to see how it goes. But I hope that there will be lots of time for questions so that we can fill in some of the gaps and so that you can understand the context of what we're trying to do with the telescope and why. Okay, so one way of thinking to start about this, like, why would we build a telescope like this? It was an extraordinarily difficult and ambitious endeavor. And one of the points that I want to start with is just that it's really important. You know, I work in the School of Science at MIT, and I believe in the value of basic science to understand some of the big questions that we have about the universe, right? Every civilization has looked up at the stars like this. This is from a beach in Australia. And you can see the Milky Way overhead. The Milky Way is much more interesting in the southern hemisphere than it is up north, because you can see those two Magellanic clouds that are down at the bottom. They're our friends that we'll return to throughout the talk. Those are two galaxies that are orbiting the Milky Way, and this arch that you see over the top is our own galaxy, which has about 100 billion stars in it, but we're seeing it from the inside of the galaxy, which is why it looks like this funny projection onto the Earth's sky. And people have just wondered all these questions about where we came from and where we're going. And they always knew that somehow it was tied up with the stars, right? Some of the first words in a lot of religions, if you look at the book of Genesis, you look at the Torah, you look at all civilizations have their creation myths that explain how the universe came to be. And what we're trying to do here is build a science-based narrative of our origin and destiny. Like, we want a creation story that tells us how the universe came about, but we want it to be in a way that's testable and follows the sort of scientific method. I mean, The secret is that most scientists don't actually do science using the scientific method, but we do believe that we should make observations that any person could go out and test and get the same result, and also make predictions that we can verify. And so we're trying to do this, not to supplant what all those other civilizations and generations have done, because that's important too. But it's just to acknowledge that part of our humanity is to wonder about this. That's what makes humans unique. And if we're going to build an experiment that's as ambitious and expensive as the James Webb Space Telescope, I feel like it's incumbent on us to frame its use around some of the big questions. And the ones that I'm going to talk about today that I think are pretty foundational to our humanity are, first of all, can we understand how the Earth, how the elements that make up the universe, and eventually how humans came about? Where do we come from, right? I won't be able to answer all of these with this telescope, but this is a long story that you can think of. All the edifice of science is basically plugging in different parts of this. And I'm going to argue that this telescope is going to tell us about the very earliest times of this, right? It's telling us about the emergence of complexity in the early universe to fill in like the first chapter. Another question that you might wonder is, are we alone in the universe, right? I think this is a pretty big one. And one that is part of our humanity. That is, is there some life beyond Earth? And I'm going to talk about how the telescope will address that question. And lastly, what will become of the Earth after we're gone, right? So I hate to say it, but we're not going to be around forever. We don't know how long it will be, but we certainly know that the Earth and the sun will last longer. And we have some expectations for what's going to happen to the solar system in its late phases of its evolution. But is there something that this telescope can tell us about what has happened for stars that are like the sun, that are older, that are going through their sort of senior phase? So these are things, I'm going to focus on these three questions. My own research focuses on the first of those. How did the Earth, the elements, and humans come about? That's why I've got it in italics. So most of the talk will be about that, but I'll touch a little bit on the other two. So just to understand this idea that it's a little bit about past, present, future. So I'm talking about past being where do we come from, present, are we alone in the universe, future, where are we headed? It's important to understand that we use telescopes as time machines. And how does this work? So I was like this animation. This is from NHK. It was a documentary made by the Japanese television station to give you a sense of what it's like to look at something far away. If it's far enough away that the speed of light even moving at the speed of light, it takes time to traverse that distance. You can imagine what we see is a picture of something as it was in the past, right? So if you take a picture of a baby, and then the light from that picture makes its way to us, and the observer is sitting there with binoculars, but all the time, the source that actually emitted the light is aging in its own way. And here it's represented as a woman who's aging and going through her phases of light. But at a later time, when we actually observe it, this person with binoculars sees her as she was a long time ago, not as she is now, right? Does that make sense? And so that's the sense in which a telescope is a time machine, that if we're looking at distances that are far enough that the speed of light is not fast enough to make the journey instantaneous, then it allows us to look back in time if we can identify things that are very far away. So it's the power to study the past. And if we want to look at the future, what we can do is look at older analogs of the Earth-Sun system that'll tell us something about what will happen. So the sun is only about half the age, old as half the age of the universe, but there are other stars around that are older that formed sooner. And we can see what's happening to them as a way of seeing what's in our future, our distant future, not our immediate future. So just to set the stage, here you can see, I have to apologize that the screen, for those of you who are here in person, is kind of out of focus, which is a little shame for talking about this amazing optical instrument. We tried to get it focused better, but hopefully if you could just move farther away if it looks like it's not in focus and squint. Those of you online should be able to see this great. But so just to contextualize, when I say we're looking into the past, how far are we looking into the past for the research I'm going to talk about today? So here's the timeline of the entire history of the universe, starting at t=0, which is the Big Bang. And the past sort of takes us up to 13.79 or 13.8 gigayears. Gigayear is a billion years. That's the age of the universe today. We can talk afterwards about how we know that. That's not so important for the purposes of today's lecture. But when I say the past, most of what we're going to be looking at with JWST corresponds to that little red portion at the beginning. So with JWST, we're going to be able to see back to when the universe was 4 to 5% of its present age. And that's when we think that the first stars and galaxies emerged out of the sort of primordial soup that followed the Big Bang. And when we first started to see things that looked like the solar system and the stars and planets that we know and love now. It took a long time for that to happen. And of course, the future is the future. We'll talk about that a little bit more. But just to give you a couple of signposts along the way, as I said before, the sun formed when the universe was a little bit more than half of its present age, 9.1 gigayears. And then the Earth formed almost immediately after that, about 100 million years. In a cosmic time scale, 100 million years is a blink of an eye. At 10 gigayears after the Big Bang, we first started to see microbial life. It didn't take that long in a cosmic time scale. Like once the Earth formed, it was pretty quick. That's quite remarkable how that happened. And then, of course, there was a long period where life was very simple until it reached a higher stage of complexity. The dinosaur extinction happened at 13.7 gigayears, and about 100 million years later, 13.79, 90 million years later is today. So that's the difference between the dinosaurs and us. And it gives you a sense of like kind of where we sit on here. We think the sun is going to go until the universe is about 19 billion years old. At which point it's going to turn into what's called a red giant star. Some of you may have understood this or heard about it before. It will become larger after it exhausts its hydrogen fuel, and eventually it will envelop the Earth's orbit, and we will die a fiery heat death. But there's some time before that happens. Regarding how JWST addresses each of these, this question of how did the sun and the Earth come to be? That was one of the big questions I posed at the beginning. I'll talk a lot about the first stars and galaxies today. That's our past. As I said, the present is, are we alone? We're going to address that with James Webb by looking at the atmospheres of planets around other stars, because we think that there's a chance in time that we might be able to detect signs of what we would call non-equilibrium thermodynamic processes, if you're being conservative, but something that would basically, it's basically chemical compounds that could only be made if there's life. That's a ways in the future. We're not right there yet, but there's a path, a scientifically credible path to investigating this with this telescope. And then in the future, what is our destiny? Can we use this to look at stars that are swallowing planets? So we'll get back to that. Now, just about the telescope. So this was a $10 billion telescope. It was about 24 years in the making. And so I just want to say, before we get too far, just thanks to all of you, right? The US taxpayers invested in this over 2 decades. And it was a lot of money. And you can think of, is this a good way to be spending all our money? It's, I think, a fair question to ask for something that's this scale. And besides the fact that I think we're at a unique moment in time where, the nations that participated in this had the wealth and also the understanding of the importance of these basic questions that we invest in that. I think that's important in its own right. But I think it's also, you have to understand that we're not just shoveling that money into a hole. It's creating a lot of great jobs for people in the aerospace and scientific industries. It doesn't come to me, but you see all these people there. Those are folks that worked on this at Goddard Space Flight Center. And that's but a small fraction of the people that worked on this. And it was really great for the US and international aerospace industry because there were parts of it that were made all around the globe. So that's actually just a model of the telescope. They wouldn't put it out on the lawn at Goddard. But that was a one-to-one scale model. The real thing is shown here in Northrop Grumman in their clean room before it was folded up and put into the rocket fairing. That's, because everybody's in their bunny suits. Also to give you a sense of the scale of what it cost you, So each of you paid about $1 a year for the last 20 years to go into this, right? Just based on the population of the US. So it's about the price of a cup of coffee once a year for every taxpayer. And so, those of us who get to use this really deeply appreciate that. And we realize that there are other things that are important too, right? So these are other things that you spend your tax dollars on. For reference, every year you're spending about $2,300 on defense, $2,300 on Medicare, and about twice that much, a little more than twice that much on Social Security, other things like that. Obviously, those things are tremendously important, right? I'm not going to argue that Webb is more important than those things, but just to give you a sense of like the scale of things, it's important to understand how your money is being spent. And this is what your contribution was, and I'm really grateful for it, as are all my colleagues. Skipping over a lot of things that led us to that point. On Christmas morning of this year, we got to enjoy the successful launch of this amazing observatory. Somehow, after years of delays and everything, it ended up on Christmas morning. I was up at 7 o'clock watching, along with about 50 of my closest friends from the Kavli Institute, where I'm the director. We set up a Zoom and everybody got on, including Maria Zuber, our vice president for research, in her bathrobe. It was great. We knew she was one of us. I'll just show you the video.
And we have engine start. And liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported. And let's go down to the floor in the Jupiter Control Center to Raphael.
So this was terrifying for those of us who've been watching this for 20 years. We basically put everything on this, right? It's like, you know, a roulette wheel where you put everything on a number or something like that, and it had to work. And it was an incredibly complex launch, I would say. Well, I'll talk about what happened after it launched, but there was this incredibly precise maneuver that it had to do to get out of the Earth's orbit. And it actually, JWST does not orbit the Earth, unlike the Hubble Space Telescope. It orbits the sun outside the Earth's orbit at what's called the second Lagrange point. And it had to be a flawless launch to get there. And it worked so perfectly that the observatory was originally carried fuel to sort of trim up its orbit and get into the right spot. And the nominal lifetime of the mission was supposed to be a minimum of 5 years, and they were hoping for 10. And the launch was so accurate, and insertion into its orbit was so accurate that it's going to double the lifetime of the observatory, because they didn't have to use any of the fuel that they had carried along board. So unless something else happens, we expect it to be around for 20 years now, with its time table limited by the fact that this orbit is not stable. You have to burn a little fuel to stay in it, because the Lagrange point is not a stable orbit. But it made this journey to an orbit that's outside the orbit of the Earth. It actually is on a line so that the sun is here and the Earth is here. JWST is always along that line. That's what the second Lagrange point means. And then what you see up here in the upper right is a diagram showing how it was folded up to fit into the rocket fairing. The fairing is just basically what we would call the nose cone that it rode in, because this telescope is 6 meters in diameter. It's too big to fit in the rocket without folding up. And this is why it was terrifying, because most of us who spend our life designing spaceflight instruments try to make no moving parts, or try to minimize the number, because every time you put a moving part, it's something that can break. But here you see the sequence of events that had to happen. So it unfolded its solar panels, and then it had to unfold each of these two shields that you see coming out on either side. This is a sun shield that protects JWST from the sun's radiation to keep it cold, because it's an infrared telescope. It sees heat, and so it always has to sort of face its backside towards the sun. Then it puts out a momentum flap to steer, and then it unrolls these giant shades. This was the part that broke during testing, actually. It was the unfurling of these shades. Then those boom arms go out, and a set of pulleys pulls these mylar sheets. It's actually not mylar. They look like mylar, but they're Kapton, silvered Kapton. So there's one on that side and then one on the other side. And then there's this moment where they sort of spring up and pop into place 7 days after launch. So each one of those is like a series of aluminum foil that protects it. Then the secondary mirror folds out from behind the telescope. And then you're going to see a radiator on the backside that takes the heat away from the rest of the instruments, deploys out. And then they'll take the two sides of the observatory and then fold them into place 13 days after launch. And then the main deployment is done. And then they insert it into the orbit in the second Lagrange point. And at that point, you just have to sit and wait for it to cool down. So it radiates all of its energy away into deep, dark space. And you can't really turn on the observatory and take observations until it has reached its operating temperature, which took a couple of months. But while that was happening, the mirrors were in a launch lock mode, just to protect them from vibrations of the spacecraft. And then they undo that locking, and then they would move them forward into their operating positions. Each one of these mirrors this sort of hexagonal arrangement corresponds to a separate individual mirror segment. And these would move forward at the rate of 1 millimeter a day until they got into their position. And they moved over the course of 2 weeks into their final position. And then the engineers at the Space Telescope Science Institute would align them and get them into their operating configuration. And while they were waiting for it to go, they observed that the rate at which they were moving the mirrors was exactly the same rate at which grass grows. And so they had made a Chia Pet version of the primary mirror that they watered on the day that they unclasped the mirrors and watched it go. And so they were working really hard for a long time, and they needed something like this to keep them going. And they did an amazing job. And I'm really grateful to all the people who at NASA and Goddard and Space Telescope who made this go. And so I'm glad to see them having fun on their Twitter feeds, things like that. All right, so that's the thing. This was an amazingly successful endeavor. So, usually when we build engineering units and things like this, we build lots of margin. Like each person who's responsible for something builds a little bit of cushion into their design in case something doesn't work. And usually what happens is most people are fine, and then there's 1 or 2 things that go wrong, and then they use up all the margin. And then that's why NASA makes you engineer it in. This is one of the few cases I've seen ever where basically everything went right. And so nobody needed the margin. It's amazing. And so I'm not one to prone to hyperbole or exaggeration, but if you see me sort of bubbling about this thing, it's because this observatory is fantastic. Let's see what it does. Okay, so we're going back to this picture of the Milky Way that I started the talk with. And I want to show you what this looks like to James Webb, and also give you a sense of this small patch of the sky that it looks at. So this is something that's not made for looking at a wide area of the sky. It looks at a small area in precise detail. So first, let me go from this all sky image to one that we can zoom in on. So let me see if this works here. All right, so there's an area that I've zoomed in here. So what I've done, let me just back this up here. So this is just a zoom in on this area that you see here is the Milky Way. And then this is the Large Magellanic Cloud in the Southern Hemisphere, and this is the Small Magellanic Cloud. And so I'm going to zoom in using an image that was taken before JWST, using the same wavelength of light. And then we're going to stop, and then I'll crossfade us into the James Webb image so you can see what the improvement in quality is. So there we go. Hopefully this is working online as well. That's not too jerky, which is great. So we're zooming in, we're zooming in, we're zooming in. Previous telescopes were pretty good. We could zoom a long way in. It's going to feel like you're still moving. It's like Star Wars. But okay, so that's the limit. And you can see that these previous telescopes, you're starting to get to the limit of what these things could focus, right? So you see that the stars start to look blurry when you zoom in enough. And so now we'll train James Webb on it and crossfade that in so you can see the improvement in quality. Okay, so that's what we're dealing with now. And now I'll zoom in to focus on a particular area. This is actually one of the first images that was released from the observatory. And it's going to look better online than it does here in person because our projector's not in focus, but we'll do what we can. There's a couple of things to notice about here. I'll show you some other images that sort of show before and after versions of this, what this great observatory can do. But the things that excited me are, if you can see up here in the upper left, this area, or look at this galaxy that's over here. See all those little dots that are around it? Those are individual stars and star clusters in these other distant galaxies that are at cosmological distances. Those are things that we were not able to resolve with our previous telescopes at all. There's no way we could do it. And then there's all these kind of crazy, weird looking galaxies like this thing up here, like what's that, right? So my professional colleagues spend a lot of time just surfing around these images, just being like, what are we looking at? Like, what are these crazy things? And that's kind of fun. And then we get serious and do our science, put our scientist hats back on. But it's really a joy to look around these and spend time understanding what this telescope is delivering. So, again, putting the scientist hat back on. So that's what the telescope does. It gives you a sense of what the improvement in data quality is that we've achieved with this new observatory. Let's go to some scientific measurements. So I'll start with one that I'll spend less time talking about. It's not my own area of expertise, but it's a big one at MIT. We have a large group of people that look at planets around other stars. We run another NASA mission called TESS, which is constantly scanning the skies to look for planets that occasionally dip in brightness by 0.1% or less, because there's another planet. Like if an exoplanet around another star is oriented edge on so that its orbit passes in front of us. We don't call it an eclipse because it doesn't block out the whole light. We call it a transit because it only blocks out 0.1% or less. Now, we've been able to look at those with telescopes on the ground and Hubble Space Telescope and other things. But what Webb is really going to give us the ability to do is examine these in much more precise detail because it's a much bigger telescope than we've ever had in space, right? So Hubble Space Telescope, which I'll call HST from here on through the rest of the talk, if I switch back and forth, you'll know what that is. That was 2.4 meters in diameter. That was exactly the size of the Space Shuttle's cargo bay, so that's what limited that. This is because this was an unfolding observatory. It's 6.5 meters in diameter, and so that means it produces sharper focused images, but it also gathers more light per second from every source that it looks at by a ratio of 6.5 over 2.4 squared. It's the area of the mirrors. What this increased area and increased super precision of working in space allows us to do is not just look at the dip of light from a planet passing in front of the star, but we are interested in studying the chemistry of exoplanets' atmospheres. And how do you do that? Well, if you think of a planet, a simple version of it is just a rock with a ball, with an annulus of gas around it, then the rock is represented with a dark shadow in this cartoon, but then the annulus is partially transparent. And its transparency depends on what color of light you're looking at, because if you have molecules in the atmosphere, they may absorb certain colors more than others. Right? This is what makes the greenhouse gas, is that methane and CO2 absorb light, or the greenhouse effect. They absorb light at infrared wavelengths, and they trap heat in the Earth's atmosphere. But if you look at it through the atmosphere, you can actually see absorption features from these different molecular species. You can do this on an exoplanet too, because if the exoplanet, the whole transit removes 0.1% of light, then a 0.1% is from that little annulus, and you could look at the color dependency of that, and then you can infer what the chemical composition of the atmosphere is. So it's hard to believe, but it actually works. And here's an example of such a thing. So one of the first spectra, well, this is called a spectrum because it's a plot of the intensity of light as a function of wavelength. And what you see, the individual dots there are the measurements from JWST, and then the blue line is a model fit of the chemical composition of an atmosphere that has water vapor. That's shown by those wiggles, right? That corresponds to molecular absorption and emission from water bandheads that are rotating. If you take the molecule, it's a polar molecule, so if you spin it, it will actually either emit light or absorb it. And these sort of up and down wiggles that you see here follow the data, which is telling you that there's water that was detected. Another way of thinking about it is that in the colors that water absorbs, that planet looks a little bit bigger than a rock, right? You can think about it that way. And that means that it has an atmosphere and that atmosphere has water in it. And so, as we all know, water is a necessary, though not sufficient, condition for life on the Earth. And we're really interested in understanding where water vapor and eventually where liquid water is. We can't probe liquid water with this method, but we're interested in figuring out where the chemical composition would support that. Another thing that can be produced either naturally or by life is carbon dioxide. So here's another example. This is actually a spectrum not taken with James Webb, but this is one taken with the Hubble Space Telescope of a different star. It's the same method where you're looking at a transiting planet passing in front of the star. And in this case, people were looking for, so the water band heads are marked with the H2Os in there. And then CO2 is shown out at a wavelength of 4 to 5 microns. You see that there's just two big crosses out here. There's one here and one there. Those correspond to the wavelengths where CO2 would be. And it was claimed that there might be carbon dioxide in this system based on this observation with the Hubble Space Telescope, but a lot of us were kind of like, maybe. And then, but it was one of the first things targeted with Webb for that reason here. So this is the before picture. And this is what the carbon dioxide spectrum looks like that was obtained in the first week of data taking with Webb. So there's just no doubt, right? So that there's things that were hard before that are just easy now. And it's going to be quite remarkable that we can look at the different chemical compositions of these exoplanets. And as we get more complex chemicals, then I think the goal is to work towards things that are biological in nature. It's going to take a long time for us to get there, And I think it's one of the most challenging observations that it'll do, but I think this could be a big part of the legacy of this observatory. So as I said before, my own group studies something different. So I study the distant past. I'm interested in the emergence of light and chemistry in the universe. All of us learned on our mother's knee that the universe started only as hydrogen and helium, and that all the subsequent elements of the periodic table were formed in the cores of stars through nuclear fusion, and then they blew up as supernova, and then seeded the rest of the universe. And I'd like to know, when did that first start happening, right? Because we have a robust periodic table now, so that this process must have started very early. Not only that, so when the chemicals were released, they were also releasing light. And if you look at computer simulations of how light escaped from the first stars, before starlight had turned on, the universe was a dense, dark place, and it was full of gas that was neutral. It was basically mostly hydrogen, but the electrons were bound to their protons. And that made the gas opaque to UV light. We call that the dark ages. But then as light first leaked from stars into the surroundings, that light would separate the electrons from their protons and it would make the universe transparent. And so basically it's like a veil that gets lifted from around. And there's evidence that this happens is that sort of light leaks out. So I'll show you what this looks like in a simulation. So you can see here on the right, actually, let me pause it here just so you can get a sense. This is a cube that's extraordinarily large on a side. So this has been simulated by Tom Abel and Marcelo Alvarez at Stanford on their supercomputing cluster. The Milky Way's size on here would be about a pixel. And what we're looking at is a representative volume of the universe, and we're going to spin it around just to change your perspective. It's not that the universe is actually rotating or spinning. It's just for visualization purposes. But areas that are black on this cube are opaque, and areas that are sort of light and white are transparent. And what you see is the transparent regions are going to grow. They start as little bubbles that are centered around where galaxies are, and they grow out to the point where they merge together. Oops, let's start that again. They're going to grow out to the point where they merge together, and then eventually when they've completely merged, then the universe is totally transparent again. So if you watch slowly, you'll see that the lighter areas are going to grow in time. And that represents photons leaking out from the first stars and lifting this veil I was talking about of opaque gas. The gas is still there, but it's been what we call ionized, where the electrons are separated from their protons, at which point the matter is no longer going to absorb light. So now you see that it's about 50% done. And then at some point, it undergoes what's called a phase transition, where the entire universe will be transparent because there's no more of this opaque matter left, because essentially the light has completely filled the universe. Okay, so here you see it. It's almost there. It's almost there. And then all of a sudden, poof, like this last little bit's going to go. And then each one of those dots that you see there represents one galaxy. So there'd be 100 billion stars in each one of those dots. Right? So that's how we think the universe was filled with light. It's the old let there be light. And it would look like this. The point is that we haven't been able to see the starlight from these galaxies before. They were just too faint because, as I said, we're looking way back into the past. We think this happened when the universe was about 5% of its present age. And we look at things, if we want to look back into the past, we look at things that are far away. As I showed, remember that picture of the baby that was aging? And the farther away you look, the more back into the past you're exploring. The problem is that as you move things further away, something that's fixed brightness, as you move it away, it looks fainter to us, right? And so to look at these things in the very early universe, you have to look at stuff that's extraordinarily faint. Also, it gets red for reasons that I won't describe too much, but what we need is a big infrared telescope in space. And now that's what we have. And so the question is, can we go and search for these things? So just from the standpoint of looking at faint fuzzy things, which is what I do for a living, so here's another example of an image taken with the Hubble Space Telescope. This is of a galaxy cluster. And just to see what it looks like as we observe the same object with Webb, you can watch it sort of snap into focus as well. So the Hubble image looks pretty good, but here's what it looks like with JWST. Okay, and so it's not just that you're seeing sharper images. One of the things that's fun is that there's this sort of iconic diffraction pattern with a sort of six-sided spike. That's how you know you're looking at a Webb image, if you see those 6 spikes. But also, it's all these little faint objects here that you can see. See these little fuzzy things that are in there? Those are the kind of objects that we're looking at when we're looking all the way across the universe. And in fact, I think I've got a better image of this. Well, I'll show it in a minute. Let me not look at that. So, so it's really great. So it doesn't show on the screen here. So I'll show, I think there's another version that will show it much better in a minute. But there's one other thing that I want to emphasize too. So we often talk about a picture being worth 1,000 words, right? I could talk about how great this telescope is, but I'd rather just show you pictures. But I also want to say a spectrum, which is basically taking the light from the telescope and putting it through a prism or diffraction grating to turn it into a rainbow. A spectrum is worth 1,000 pictures. Because basically what we do is actually take the light from the telescope, and then we just slide a prism in front of that focal plane. And then it's going to take each one of those stars. So we take a picture first to contextualize where we are, but then we put this prism in front, and then each one of the stars turns into a little rainbow like that on the detector. Okay. And basically we've got the prism that's going that way. And if you sort of, it's a little bit light in here to show it, but if you kind of go halfway through this animation here, maybe you can match up that this spectrum here corresponds to that star. And then there's another spectrum corresponding to that star. And then this one corresponds to that star. I've just cross-faded them so you can see that basically all we're doing is you get a bunch of these individual rainbows that all overlap each other on the detector. And why do we do this? Well, it's because these spectra allow us to measure very precise distances to each one of those objects. It also allows us to measure precise chemistry of those objects. We can see individual elements, oxygen, neon, carbon, helium, hydrogen. And we can also measure the temperatures of stars using their spectra, because the hotter a star is, the bluer its spectrum looks, right? You've seen things that are white hot or blue hot. We can actually measure the relative numbers of photons coming in of different colors, and from that deduce what the temperature is of an object that's all the way across the universe. It's pretty remarkable that it works that way. And so I'm a spectroscopist. It's what I do. And this is how we use the telescope. So we have to take an image first to measure things in a couple of different colors, and then we slide in the prism, and we take these spectra, and then we have to disentangle all these rainbows that are on top of each other on the detector. This is actually just a simulated version of it, just to give you a sense of what it looks like. But now we have some data. And so here I want to shift to the part of the talk where I'll explain a little bit about the data that we have. As Megan said, one of the things that's fun for me is I've got 100 hours worth of time. My team and I are going to be observing 5 different fields at 20 hours each. And the first of our data arrived in August 21st, a month after the telescope was commissioned. So it's really fun. We're some of the first users of this thing. We've been planning since about 2015 for these observations, so it's been a long time coming. And of course, it was while I was on vacation, but whatever. We're back at it now. So this is the first field that we saw. It's very special. You might ask, how did we pick this field? Like, how do we know where we're going to point the telescope? There's a very special object in this. I told you that I study things that are all the way across the universe, that are very, very old. One way that you can look for things that are very old are that they have very red colors. And there's one special object here, which if I can get actually, I think I have to use this thing. So this thing right in the middle here. So that is a really bright object, but it is very far away. Usually things that are bright are close, right? So these things that have the spikes on them, these are all stars. They're in the Milky Way. So we have to look through the Milky Way to see things that are far away. This thing looks like a star, but it's actually a black hole. And it's a black hole that is the brightest one that we know of in the early universe. We're seeing its light as it was 95% of the way back to the Big Bang. So this has a redshift of 6.3, if that means anything to you. But it's an extraordinarily distant object. We can talk a little bit about how we found it. But the point is that we knew that there was something there in the very early universe. And where there's a black hole, there's probably a galaxy and stars. And where there's a galaxy and stars, there's probably other galaxies and stars because things clump together. And so we knew there was something interesting going on over there. We had found it a long time ago and decided to train the telescope at that location of the sky. You might ask, if there's a black hole, why is it shining so brightly? I didn't think black holes produce light. We can talk about that in the questions afterwards if you like. But basically, it's not looking at stuff that's inside the black hole. It's stuff that's on its way in. It hasn't quite reached the event horizon yet. And so it's heated up and it shines very brightly. It's a short answer. Okay, so there's what an image looks like. This is about 10 hours worth of data. This is 10 hours with this is already deeper than anything Hubble ever took. So that was kind of fun. It's more sensitive than it was advertised to be by the engineers who built it. So it's always nice when it works in that direction. Here's another way of looking at. I promised you that I would show you a better version of a before and after to show you the kind of galaxies that we're interested in looking at. So here is an image with the Hubble Space Telescope. Here is that black hole that I was telling you about before. I think this is 4 orbits with HST. And so it's a pretty deep image taken at roughly red wavelengths here. And now I'll show you what the same image looks like as seen with JWST. And there it is. And so now you see that the quasar or the black hole is shown right here. It's actually so bright that it saturated the detector, but that's okay. We can back out the flux at that location. But what I'm interested in, see all these little things that are around it, these little tiny blobs. As I said, I like to look at faint fuzzy things. So like, look at these two here. See this thing and this thing? I'll go back to the image from Hubble. They're just not there in the Hubble Space Telescope image. And now I'll go back to James Webb, and there they are, right? These two here. So those two objects are sitting actually behind the black hole. So what you're seeing is starlight and nebular light from galaxies that are at a 95% look back to the Big Bang. So we're looking at individual objects now, and it's just obvious that they're there. These things were not visible in any telescope that we had seen before. And it's just easy to see them. And it's just remarkable to me. You know, I've spent decades trying to look for these things with other telescopes. And it's a joy to see it come in and be this. You know, usually we're working at the edge of signal to noise and like wondering about the significance of our detections. And we'll get there, of course, every telescope, we always get there. But for right now, it's just fun because things that were really hard to do before are just shooting fish in a barrel. There's the image. Here's those spectra. So I showed that rainbow image before. Here, when you put the prism in front of the focal plane of that image that I just showed you before, and you spread out all the light, it looks like that. So there's two modules. These correspond to two different detectors that are next to each other in the JWST focal plane. So each one of these horizontal lines represents one object. This object here, see this one here? That's the black hole. And so it's sort of, everything is turned into a line because we don't actually get rainbows, we get everything in grayscale. And so we've been working around the clock for the last 6-8 weeks, trying to process these raw spectral data that look like this into something that actually is scientifically, you know, it's a scientific data product that we can actually do our final measurements on. Let me just see how I am on time. I'm good. Okay, so we basically take all these overlapping things and have to disentangle them and turn them into interesting objects. So here we're getting a little bit into the weeds, but I can't help showing this. A couple of things that are real data here. So this is no longer simulations. This is stuff that the world hasn't seen before, actually. So the bottom line is it's really easy to spot what these primordial galaxies are with JWST. They're everywhere, and the detections are not marginal. They're really strong, actually stronger than the theory and expectations had predicted. Just to show you what it is that it looks like. So you see this one here, that this is an image. This is just a cutout of the image of one of these distant galaxies. And you might say, like, how do we identify that it's really far away? And the way that we do that is that as I said, each galaxy has its own spectral fingerprint. Like you've probably seen on like CSI shows where they take a little sample of gas and they put it into the thing. They say, we want to look at the chemical composition. So we're going to put it into the spectrometer and we shine light on it. And then it's going to tell us, you know, something that it was going to help us solve a crime. So we can do that with light that's coming from these distant stars. And if there's a nebula around those, they actually shine brightly in this very specific way. So these are actually, what you're seeing here this is a spectrum. So it shows wavelength on the x-axis and intensity of light on the y-axis. And you see that there's these 3 spikes here. And they correspond, the spacing and relative heights of these is fixed by atomic physics. And it tells us, if you see these 2 lines in this spacing at this line ratio, that's oxygen. And then likewise, if you see this line here, there's hydrogen. at the same distance as this oxygen. And we look for these triplets of lines or pairs of lines that are sort of a pattern recognition. And in the raw data, they look like this. So you see the little vertical hash marks here. Those correspond to the locations of these two oxygen lines, this one here and this one there. And you see what we're seeing are the actual rainbow images off the detector, where the wavelength of light, the color, is going from left to right. And then when you see a dot in there, that corresponds to the location where you would see one of these little emission lines from the distant galaxy. And here's just a montage. It's basically a rogues gallery of these things for different galaxies that we see in the image. So you see that they move from left to right. They're basically getting redder, but you can see that we're matching, 1, 2, sometimes we see the third one. Every time you see that pairing of objects, that corresponds, and then we see it, a galaxy at that location, we can measure the distance of that galaxy. And we know that they're very far away, and the redder they are, so the things at the bottom of this montage are more distant. And this is just a zoom in. This is in one field that we looked at. I had seen in my entire career 0 of these objects before this month. And then in our first field, we found all of these. Those of you who are closer can see that see these little doubles that go down here and down, 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 all the way to very early times here. These reddish ones at the bottom are the most distant. So these things they're everywhere. So that's pretty cool. In case that all sounded like Greek to you, let me try to contextualize it a little bit. As I said before, we're going to come back and visit the Magellanic Clouds, right? They're our nearest neighbor galaxies. The Magellanic Clouds are 2 small galaxies that are falling into the Milky Way. They'll merge with us in some period of time. And you can see them from the southern hemisphere. And this image shows something that looks like the Milky Way. It's a nearby galaxy that's NGC 3953, but if you could see the Milky Way from the outside, it would look about like that. It has about 70 billion stars in it. And the location of the Earth relative to the center of the Milky Way is shown with this red dot. And then this shows the Magellanic Clouds and approximately their correct size and distance in relation to the Milky Way. And they're orbiting each other and they're on their way in. So the small Magellanic Cloud is smaller, as you would expect. This has about 500 million stars, so 500 million stars in it, and it's forming stars at a rate of 1 every 20 years or so. The Milky Way is forming about 1 star per year, but it's much bigger. The large Magellanic Cloud has about 2 billion stars in it. So that's just to kind of give you a sense of how these are. Let me show you the cutouts of some of these objects with JWST that we're finding. What I'm calling a galaxy is really kind of, I like to think of them as baby galaxies. So this is just a montage of a few of them, and I've scaled them to approximately the same size as the other things in this image. It's not precise, but it gives you a sense of what's going on. So when I say I see a galaxy here, you should not be thinking that you're seeing another Milky Way, right? You're seeing something that's much smaller than that. And in fact, it's only about the size of like this star cluster in the Milky Way. Or maybe even the small Magellanic Cloud is not so different. If you look at the size of these, so these have about 100 million stars in them. So they're about a factor of 5 smaller than this in terms of number of stars. But they're forming a lot more stars per year because they've just turned on. They're forming between 5 and 30 stars a year. So this is the way to think about them. They're things that are going to become galaxies as we know them, but we have to sort of shift our mind frame to think that they're not really there yet, right? They're just starting. And I'll show you a simulation of how galaxies form so you can get a better mind's eye picture. But the other thing that we can do is use very detailed diagnostics. We get so much information from JWST that we can build a mind's eye picture of these early galaxies. So here's, if you could observe, this is actually real data is shown with the red points here, and then these little dashed lines here. I'm not going to explain what they are. If you want to know, I can tell you afterwards. But we actually fit spectral models to each of these galaxies because we add up hypothetical populations of stars to build something that matches the observations. And we can figure out by what matches the observations, sort of what went into the recipe to make this galaxy. And so these numbers, which aren't going to be meaningful to you as they're presented, they are meaningful to me. And I'll just translate them for you. What it means is that this is a particular object, which is a real thing we saw with JWST. We're seeing when the universe was 880 million years old, 6% of its present age. This galaxy has 30 million stars in it, which is only 0.04% the size of the Milky Way. So it's much smaller than the Milky Way. And this is typical of these early universe galaxies. The galaxy itself is only 14 million years old. right? That's less than the time between the dinosaurs went extinct and us today, right? It's a blink of an eye in cosmic time. So it's very young. It just started turning into stars at the time that we're observing it. Remember, we're observing it as it was when it was a baby, not as that old lady. We know that the galaxy is producing a lot of light from hot stars based on this number. And we also know that the stars have 10% as much iron as the sun. So the iron is basically what's produced in those stars. So the point of this is just to say we get a lot of information. In order to make these models, we actually need a lot of computing power. And something that's kind of interesting is that, whoops, I went the wrong way. We have a computing center that MIT owns out in Holyoke, Massachusetts. It's in this building here that's run entirely by water power. It's kind of fun. So there's a canal that runs on the Connecticut River, and it goes through here, and then the water flows underneath, and it runs generators. We use electricity to run the computers and to cool them. And we actually use those to calculate these information about these galaxies in the distant universe. Here you see some of the computing that's happening there. We moved them from campus out there because we're trying to reduce our carbon footprint. So it's 100% green energy, which is kind of cool because before the computing power it would take to do this is similar to the amount of carbon that we burn in all of our air travel. Computers are very carbon intensive, which is interesting because we're using it to observe carbon when the universe was 5% of its age. But anyway, there it is. But then just to go back to this mind's eye picture. So this is actually a picture of the Small Magellanic Cloud, this one I've been telling you all about, seen up close. And when you see those little bright emission lines, those spikes that I showed you before, what you should think about is that what you're really seeing are these areas here. You're seeing only nebulae. It's like what you're seeing is a galaxy that only has nebulae and no stars. I would think if you were in that galaxy, the sky would be very beautiful. It's just that it's too young that nobody was around to see it, sadly. But if you imagine this image where you take away all the stars and all you have are those gas clouds that are lit up by a very small number of stars that are sitting inside them that you can't see. I think that's kind of what that galaxy would look like if you were sitting inside of it. But this is all brand new. Like we're still trying to figure out, like, this is a hypothesis that we were talking about this morning, right? This is not settled scientific fact, but we're trying to understand what this observatory is giving us. As I said before, the simulations lead us to expect that galaxies shouldn't have been fully formed at this epoch. They shouldn't be around yet. So I'm going to show you a numerical simulation of how a galaxy forms, like the Milky Way. So this was run on a supercomputer. And the point here is that the things that we're looking at with JWST, they're like baby pictures of galaxies, right? Or even embryos. So this is just a gas density and temperature simulation. But if you turn this on, you basically put in all gravitational physics and you watch how stars form. They heat up the surroundings, and that makes the temperature go off. It looks sort of like fireworks. But what you can see is that the gas is actually collapsing onto this area. This expanding circle is sort of like the radius within which gravity acts from this galaxy. But you see over time, it settles into something where there's a little disk in the middle of it. The disk is much colder than the surroundings, and that's where the stars form. So this disk represents the Milky Way as it would be today, okay? And so that's how a computer tells you that a galaxy is made. Is made by merging a bunch of smaller things into a big thing. And what we're doing with James Webb is literally taking this, right? This is at 100% of the age of the universe. And I said it was at 5%. So we can just rewind the movie back. And so we're looking at the universe when it was about like that, right? And so the things that we're seeing and calling galaxies are like these little pearls that you see along these filaments in the simulations. They're just starting to form stars, but they haven't yet become what they're going to be, right? They haven't reached that yet. And being able to study that, as I said, we're telling the first chapters of the story of how the Earth and the chemicals and the planets and humans came to be. And it's because this is when the complexity first started to emerge, right? We haven't gone all the way forward to where all these little things merge into a much bigger object, and then they cool, and so on and so forth. And eventually they form the galaxies that we know and love today. Okay. I'm going to skip over this one. This one's kind of fun, but it's a little too in the weeds, and I want to finish up and leave time for questions. But I'll mention one more thing. I talked about, so that's the past, right? The present, exoplanets. The past was all this stuff that I do. I love doing for a living. The future, what's going to happen to the Earth once the nuclear fuel in the sun runs out? As I said before, the sun's going to expand and engulf us. Nobody's ever seen that before. It's kind of a theory tells us that should happen to stars. But we've never actually seen that happen. So a postdoc that works in my group has actually found what we think is the first detection of a planet being consumed by its host star. This has been predicted forever that this would happen. But you can see it here. So here's the title of the paper, An Exceptional Infrared Transient from a Star Engulfing a Planet. So here's the before picture before it happened. It's too bad it's out of focus for those of in the room. But of course, if you want to find the object, you just look for where the arrow is pointing, and that'll tell you. So there it is before, and then it gets brighter after this period, and then we can see it brightened by a little bit. And based on how much it brightens, it tells us how much energy was released. Is something merged into that star, and we can tell how massive that something was by how long. I think of it as sort of becoming bloated or like belching, right? That's basically when this thing goes in and the star gets a little hotter and it expands a little bit. It's just kind of like, it's like a bad meal. And then it stays in that mode for a couple of months to a year. And based on how long it stayed expanded in that bloated phase, we knew that it's something about the size of Jupiter to maybe 1/10 the size of Jupiter is what went in. So we're going to be pointing James Webb at this because it's a new discovery that's happened since then, and they had discretionary time. You have to look at this with infrared eyes. Only James Webb can see it, and so that's going to be something telling us about what our future is going to be addressed by James Webb also. The last thing I just want to say, sometimes people wonder, how did I get time on JWST? How did this come about? And I just want to say something that's important here. It's not like this just happens out of the blue. We've been working towards this for a long time. And it's really that MIT has invested in facilities over decades that allow us to do the research that we have that sort of helps us discover interesting things that we can then look at with these amazing new facilities. So this is a picture of the Magellan telescopes. It's a pair of telescopes. We have a 10% share in Chile. It's in the Chilean Andes. There's the Milky Way overhead, and the Magellanic Clouds are friends. They're the Magellan telescopes. And I call this like the currency that we bring to the table, because we brought, so I helped I actually built an instrument for this telescope. So this is actually what it looks like inside the dome. On the right, that's me on the crane putting this instrument on, and left, it's us putting it together in the lab. And that instrument was used to discover the objects that we are now pointing James Webb at. And we were able to bring that to our collaboration, that we had excellent data on these that we had taken with our facilities. And it's really important and kind of a privilege to be at a place like MIT that invests in these things that allow us, it puts us in a position to do this kind of science that's new and impactful. And continuing to invest in that is something that's really important. I will say that, I say this, that's, my team, but it's really an interesting thing is that our team is all across the globe. And so I just want to mention, this is the group of people that's working on this James Webb data. The Christina Eilers and I, she's a postdoc, a Papalardo fellow that works with me at MIT, and Ramon Bordoloy was a former postdoctoral fellow at MIT, now at NC State. And then we have colleagues at ETH in Zurich and at Nagoya in Japan. And so scheduling telecons is interesting for us, but we do it at inconvenient times for everyone. So it's just kind of fun to work with these folks. So it's been a really fun, 6 weeks to a month or so. And I'll just leave you with saying this comic that I saw from XKCD that kind of sums it up best, right? They say the best camera is the one that you have with you, but it's just wrong. The best one is obviously JWST, and there's lots to come from this. So thank you all for your attention, and look forward to answering some questions.
Okay. Well, I'm sure who wants to who has the first question? I'll see if I can hand the mic down.
So I just don't understand. You said that the Webb is an infrared telescope, and then you show us these pictures with different colors in the visual spectrum. So how does that? What's the translation between the infrared detection and these beautiful colored pictures that are all different colors?
Basically, we just totally fake it, right? Those images are taken at a wavelength of 1 micron, 2 microns, and 3.5 microns. And we turn them into color images because there's 3 different infrared colors. But of course, your eye wouldn't see any of those. Your eye sees the colors that the Hubble Space Telescope sees. It's really, I do that. It's really instructive because you can see the colors, the relative colors of things is still important. And we have quantitative ways of measuring color too. We don't just look at pretty pictures and say, oh, look at that one, right? So we actually measure how many photons came in. The newspapers are doing all the same thing. Totally, yeah. Yeah, so these are all red words of a micron. So your eye would not see any of them. But that's part of what makes it so powerful, right? If you want to look at the early universe, you've got to look in the infrared because the light is actually stretched by the expansion of the universe on its way to us. And so if we looked at with optical eyes, we'd see nothing. That's a good question.
That's more questions. Do we have any questions online, Mia? Oh, Stephanie, could you? Sorry.
So one of the questions we have from online is how soon after the Big Bang was light created that the JWST could see?
So the earliest things that we've seen are from about 3%, 90% look or 97% look back time to the Big Bang. And so that would be about 300 million years after the Big Bang. James Webb has not only taken images of those, but they've taken these spectra. So we see lines from them, which means that we know that the distance is correct. We think that there are objects that are earlier and that we think that James Webb will eventually find them, but it's been operating for 6 weeks. So we'll get there. I mean, if we've got all this in 6-8 weeks, there's a lot coming.
Gentleman there. Next.
When you look out at this 97% or 3, depending on which direction you're measuring from, are you seeing any differences in the directions, or is it pretty similar, at north, south, east, west, around the whole sphere?
Yeah, so the question, I guess you had the mic so everybody heard the question online. So far, what can I say? We haven't looked at enough places with this telescope yet to know. It's really brand new. So I guess we've looked at 20 fields that are sort of similar to these and randomly placed positions around the sky. And so far they all look consistent with each other. I don't think we've spent a lot of time comparing them in that way just yet. I think we're analyzing them one by one. Somebody will go back and look at the ensemble at a later time. And it's true that, for decades and decades and decades, people have looked in different directions and the universe looks the same in every direction. Once you smooth it over a large enough scale, right? You've got to kind of defocus your eyes a little bit, and then the universe looks uniform and the same in every direction. With the one exception that it looks, there's a weird thing where it looks hotter in one direction than the other direction, but we understand that very well. It's because the Earth is moving in that direction because of its rotation around the center of the Milky Way. And so we're moving with respect to the rest frame of the entire universe. Once you subtract that out, then the universe looks the same in every direction to within every measurement that we've been able to take. James Webb it's too early for James Webb to weigh in on this, but we kind of expect it will continue.
All right, we have a question over here.
Actually, 2 questions. Early on, the James Webb was hit by a micrometeor, which apparently wasn't really predicted. I was hoping you could address that, the implications of that in the long term. And the other question is, in the lay press, there have been articles written by apparently a minority of scientists that James Webb is seeing galaxies that are older than predicted by the Big Bang. They should be. Can you address that controversy as well?
Sure. Let me do them in reverse order. So no, those are both good questions. It's always scary when you find an object that's older than the age of the universe. This has been something that's happened over the course of time. There's 2 or 3 instances in the course of my career where this has happened. I would say that that result is no longer holding up. So that comes from these, where did I have? See this model here where you fit, so you're fitting a very complicated model to 6 data points. And the model has more than 6 parameters. But those of us who grew up in what's called frequency statistics would always say, like, you shouldn't fit more parameters than points in your model. It's a little different than that because you're not fitting, the parameters you're fitting are not orthogonal to each other and they don't span the space, if that's meaningful to you. But the point is that I think what they were fitting was probably under constrained in the sense that they were allowing, there's other solutions that fit those same data equally well. If you want to say something's older than the age of the universe, it's one of those extraordinary claims require extraordinary evidence. And if there's another solution that fits as well or better, then usually we would reject that. It was just that I think they did it quickly because they were really excited about the result. It was like a day after the stuff was published. I think most of us are not losing sleep over that one. But it's always interesting. That's the way the scientific method works, right? You put stuff out and see what happens. And I don't fault folks at all. Like, I think it's great when people get into they mix it up, and see what happens and put themselves out there, and then see where the chips go down. With regard to micrometeorites, yes. So I remember when we first saw that, there's an emoji that looks like a person's eyeballs, like really wide. And when we first saw that, all of the Slack, we've got a Slack channel for our collaboration since we're spread over the whole globe, and there were everybody was kind of nervous about that. It seems like the observatory is fine. To my knowledge, there hasn't been another one. Every once in a while you get unlucky, right? So there's always this worry that you turn something on and you see something sooner than you expected, and then everybody goes back and calculates a rate of expected event hits based on one, just because that's what we do. So far, usually the cautious counsel is just to wait and then see what the real rate is. I haven't seen the folks at Space Telescope being alarmed about it. It hasn't affected the optical performance of the telescope so far. And I think we just have to wait and see. Right now, I think most people are feeling like that was just bad luck, but it's going to be a little while before we know for sure. So fingers crossed on that one.
Okay, another question from online. What format does your team get the data in, and how large are those data files?
Well, that's a really good question. We get them in this weird format. Okay, let me back it up. So there's something we call the flexible image transport system that was invented in the 1970s. It's called FITS. And the FITS standard was originally developed so that you could send the individual units of data on paper punch cards that went into machines that would only program in Fortran. But somehow this has stayed with us. But so we use these things. I mean, they're not on punch cards obviously now, but the format they come into is like an image cube. So it's the detectors on the spacecraft count in what's called photoelectrons. Every time a photon hits the detector on the spacecraft, it liberates an electron hole pair in a semiconductor, and then that's captured and it turns into a voltage on a little capacitor in that pixel. And so then we convert that voltage into the number of electrons that have hit the observatory, or the number of photons that have hit the observatory. And then we get down count rates of those. And they're like three-dimensional cubes because it's counts it's 3 dimensions because an image looks like this, right? So there's 2 dimensions, there's X and Y. And then the 3rd dimension is basically the height of, you could imagine turning this on its side, and the height of that, or the intensity, is the third number. And so we get that as a function of time. And then we take the cubes and we process them. So how big are they? So these are 2000 by 2000 pixels. So that's 4 million pixels times 2 bytes. So it's 16 bits. So what's that? I can't do the math in my head. I'm sorry. Was that 16 megabytes? Do I have that right? But then you get that 16 megabytes like 30 times for the time series. And then there's 4 detectors. I've shown 2. And so it's actually a fair amount. And also you have to telemeter that down over the deep space network from the second Lagrange point. So it's actually quite a large amount of data that needs to come down. And it takes a long time to run through the computers to turn it into the final data product that we have. Sorry, this is not a great answer to your question, but you sort of get the idea. It's like some janky system that we've like put together over decades, but it actually is pretty robust. And the data volumes are big, but what we're seeing is not big data like, the sensor data that you need to drive an autonomous vehicle or something like that. We're not doing that.
Okay, I think we have time for maybe one more question.
Thanks so much. Maybe on a more personal level, taking this for a spin, I saw that you're into amateur astronomy. So what's it like now? Are you still interested or fascinated by amateur astronomy, or what's exciting there?
Oh, I still love it. Yeah, I mean, I wish I got to do it more. So I still have more telescopes than I would like to admit in my basement. I don't really. So I have a sort of second job that I do, which is still. So it's not just astronomy. I like building telescopes, and so I guess I mentioned it here, like with with this thing here. So I still build stuff like that. And that sort of stems from my old passion of grinding mirrors in the basement with my dad. That was a really fun thing that we shared over the years. And I still like doing astrophotography, like for the solar eclipse. I had a telescope out and took a lot of pictures with that. And when I go camping, I still do that. You know, the skies aren't so great around Greater Boston, so I miss that a lot. But it still makes me really happy. That's how you know you're in the right job, right? If you know, every job has things that you'd rather not be doing. That's why you get paid. But this part of it still makes me really happy in the same way that it did when I was growing up. So yeah, no, thanks for asking. That's a nice question.
Okay, I think we have to wrap it up now. For those of you who are here with us in the room, we still have some refreshments to out in the lobby to enjoy. And I'd just like to say, thank you very much for giving a look at what you do, and just like to say that you're not just looking at blurry objects. You are actually looking at, you know, things that have happened a long time ago in galaxies far, far away.
Oh, there it is.
Yeah, I know. It had to be said. I went there. Just once again say thank you very much, and here's a token
Thank
of
you
the
so
club's gratitude for helping us out. Yes.
Thank you so much.
Thank you. Thank you. Thank you. And I'd also like to thank the volunteers who have helped out with this tonight. Mia, Stephanie, Bob, Bonnie, and Helen. I think thank you all. Thank you so much. This was really great. And I hope to see everyone back here in November when we'll talk to Linda Griffith, and we'll talk about microscopes instead of telescopes. Thanks.